Today we're going to look at common logs and natural logs. Those are two types of logarithms. And the learning target would be that you can solve any exponential equation using either common logarithm or natural logarithm. All right, so on your calculator, you have both of these buttons, log and common log. We'll talk about common log first. Anytime you see a logarithm written out and there is no base number written, as in this first problem right here, that means, or it's understood then, that the base number is really 10. So if you don't see a log written, that means it's a base 10 common. And the reason that one's referred to as a common log is because we use base 10 as our counting system on Earth here. Everything's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it goes on to the next thing. Also, it's used all the time in science when you do scientific notation. We use base 10. Now, you can do these. There is a common log button on your calculator. If you are using one of these TI-30 calculators, common log button is right here. If you are using a TI Inspire calculator, it's on there. It's a little bit harder to see. It's on top of the 10 to the power button because it's kind of the opposite of it. So you have to hit Control and then this button, and then on your screen you should see common log pop up. On the TI-83 or 84, your common log button is right there. All right, so let's try doing one of these. I'm going to be using a TI-84 here. So on your calculator, you want to type in, or hit your log button, and then type in 3, and it will take the common log of that number. So it's about 0.477. And I think here it says to do it for 4 decimal places, so we write it as 0.4771. It's approximately equal to that. Okay, why don't you pause it quick, try log of 0.2 and see what you get for that one. All right, if you do that, you get, again, hit your log button of 0.2, hit equals, and that should come out to be about, to 4 decimal places, negative 0.699, and if we round it would be 0. Okay, so that's using common log, and that's where you find it on the calculator. All right, so we're going to use logs to solve here, and you can do that by solving out a problem like this. So thinking back, if we wanted to solve for this problem, 3 to what power equals 27, we looked at a way to do that by getting the same base number. Okay, so we would want to think on this problem, 27 is the same as 3 to what power here? What power of 3 would equal 27? Well, 3 to the first power equals 3. 3 squared equals 9. If you do 3 to the third power on your calculator, you see that that does equal 27. So we can write 27 the same thing as 3 to the third power. Well, if we want to solve this now, if we know these base numbers are the same, that means the exponent should be the same too if these are equal or equivalent, so that we would know on this problem that x equals 3. All right, we're going to show you today how you can get that same answer by using a process that involves logarithms. So what we're going to do on this problem is start by adding in the common log of both sides. So we're going to add in log to the left side, and we're going to add in log on the right side. And you can do that. You can add logs in as long as you do it to both sides. Now, if you go and use one of the log properties that we talked about, anytime you have a log and there's an exponent we talked about, that's the same as that exponent times your logarithm. Okay, so now our problem looks like that. Now, if we're going to solve for x, we can, because now x is being multiplied to this log. If we divide by log 3, now we can solve for the answer. So on our calculator, if we take log of 27 divided by log of 3, it should give us the same answer we got before of 3. Let's check it out and see that it works. So on your calculator, you want to hit log 27. Make sure if your calculator puts in parentheses like this that like an automatic parentheses, that you close it here because we want to shut that logarithm off now. Then hit divided by, and then type in our other log. So log of 3. And if we hit equals, you see that the answer comes out to be the exact same thing as we got before of 3. So that's another way you can solve these logs other than finding the base number. And in fact, we're going to need to use this process because you can't always use a base number to help you out, as in the next problem. If we look at the next one here, we want to be able to solve what is 3 to the 11th power going to be, or 3 to what power equals 11? Well, we just went through and we know 3 squared equals 9, and 3 to the 3rd power equals 27. We just had that, but neither of those are 11. So that must mean this exponent is somewhere between 2 and 3. It's going to be some kind of decimal number, fraction in between 2 and 3. How do we find out what that is? Well, we can't make the base number the same in this problem, so here's where we're going to use that log process we just did. Start by doing the logarithm of both sides. So we're going to add in logs here now on both sides. Okay, now we're going to use our log property that says that's the same as our exponent times our logarithm. And now if we divide by the log that's on the side of our x, we can come up with our answer. So x here is going to be whatever log of 11 is divided by log of 3. So on our calculator, if we go ahead and type that in, we should get the answer. Log 11, close that parentheses up, divided by log 3. And the answer comes out to be about 2.18 or something like that. So that's our solution to this problem. That's what that exponent is, approximately equal to 2.18. And that is between 2 and 3, like we said, because it's somewhere between these two numbers. All right. Next one, number 4, is pretty similar. See if you can pause the video. Why don't you try solving for this exponent and see what you get. All right, let's see how you did. First thing, add log to both sides. Okay, we want to now take our exponent, move it down here using log properties. And last step here, now we want to divide both sides by log 6. And if you go on your calculator and do log 42 divided by log 6, you should have gotten approximately 2.09 as the exponent. All right, so that's where logarithms are useful. They're the opposite operation of exponentials. Another type of log that we're going to be looking at is what's called the natural log. And the natural log is a logarithm where the base number is e, which is referred to as the natural number. That's why this is called the natural log, because e is the natural number. And e is one of those irrational numbers like pi. Remember, pi is equal to about 3.1415, and it's one of those repeating decimals that goes on forever. The natural number e is also an irrational number, and it's equal to about 2.7182828, and it keeps going on forever too. It's on your calculator. If you go on your calculator, on the TI-84 here, it's right under your log button in blue here. So you have to hit your second button and then hit your that button underneath the log button, and it'll pop up with e. Now it puts an automatic exponent. If you want to see what e to the first power is, or e, it comes out to be 2.71828, same thing I had written on the screen there. So that's what the natural number is equal to. So that's the base number when you do a natural log. Now, because natural log is another one that gets used very often in mathematics, it has its own notation, and it's ln. So whenever you see ln written, that is the natural log. And that one is on most calculators too. Okay, so natural log button on TI-30 is right there. On TI Inspire, it's also on there. You have to hit Control again, and then this button next to where you see the exponential e, ln's right above it, because ln is the opposite of an exponential. Same thing on a TI 83 or 84, there's your ln button there, natural log. So let's go and try out some natural log problems and see if we can evaluate them here. So if you want to do e to the second power, go on your calculator, find your e. On a TI-84, you're going to have the second button and then your natural log button, and hit the exponent of 2, and you can get it. Looks like it's about equal to 7.4. We'll round off here. E to the negative 1/3, you do the same thing. Select that exponential e, the natural number, and then type in negative 1.3 as your exponent. Hit equals, and you can get that. It looks like it's about 0.27. Now natural log. Natural log, same button, you just don't hit the second button now. Natural log should pop up as ln on your calculator. Type in the number you want to take the natural log of. Hit equals, and looks like this one's equal to about 1.4 approximately. Okay, you can do it for decimal numbers too. Type in, hit natural log of 0.05. We get about pretty close to -3. All right. So we're going to use natural log now to solve some problems too. If you look at the graph of e, like e to the x, y equals e to the x, this is the blue graph you get here. Okay, the same blue graph is on this graph over here too. That's the same graph of y equals e to the x. If you graph out the natural log of x, you get this red graph right here. Notice it's the same graph, same shaped line. It's just that it's a reflection over this line, y equals x. And whenever you get a reflection over y equals x, that means that these two functions are inverses of each other. Okay, remember talking about inverse functions? So y equals e to the x and y equals ln of x are inverses. They're the opposite operation. So what that means is you can use natural log or e to undo each other. So in problem A, we can solve this one out by doing natural log of both sides. So just like we did in those other problems, instead of adding common log, anytime you have e, you want to add in natural log. So we're going to natural log both sides here. Then we can use our property of logs to move our exponent down. So now we got x times ln of e. And here's the nice thing, ln of e, natural log and e are opposites. If you go on your calculator and do natural log of e to the first power, you see that it equals 1 because natural log and e are opposites. So basically that cancels out or is out of our problem, and x here is going to equal the natural log of 5. So that would be the exact answer. If you want to see about what that's equal to, now you can just hit natural log 5 on your calculator and see that it's about 1.61. Okay, same thing if we have this problem in B. It says natural log of something equals about 0.6931. If you want to find out what this is, what are they taking the natural log of here, you can do that by knowing the opposite. Remember, natural log is really log base e. So if we want to solve this out now, do the opposite. Okay, if we change this from log form to exponential form like you did earlier in the unit, that means what we're taking the log of x would be equal to our base number. That's our base number. So our base number on this side is going to be e, and then this number 0.693 becomes our exponent of that base number. So x is going to be equal to e to that power. E is the opposite of ln. So anytime you have ln, if you just take e to both sides, That cancels out. You got x, and you just got to do e to that power. So if we go on our calculator, select our exponential, and type in the exponent of 0.6931, we see that this is approximately equal to 1.99999, which is very close to, or approximately 2. X is about 2 here. All right, we're going to use that thinking then to help us solve some problems where we have exponentials. So anytime you have an exponential with base e or the natural number e, use ln. They're opposites. So just like we would do in this problem, multiplying, okay, the opposite of multiplying is division. If we have something squared, we know the opposite of that is to take the square root. So square root and power 2 are opposite. If you're doing a log problem, then the opposite is to do logarithms. So exponentials and logs are inverses. All right, and since e, the natural number e, and ln are inverses, anytime e is in the problem, make sure you select natural log. All right, let's try a problem out then. Number 6 wants us to solve what is this equal to. So first you're going to treat this like an algebra problem. You want to get the part with the x by itself. Now x is an exponent here, but we still want to get that little part by itself first. So we want to do it just like an algebra problem. Start by adding 7. Then we got to get rid of this number that's being multiplied by dividing. And so now we got e to the negative x equals, if we divide that out, we get 1.8. Now, how do we go from here? Because this is kind of the part you get stuck. What is that exponent? Well, we're not going to be able to solve this unless we do the inverse. And the inverse of e to something would be to take the natural log of both sides. So at this point in the problem, we're going to take the natural log of the left side and the natural log of the right side. Whatever you do to one side, you got to do to the other. Now we can use our x or our log properties, move our negative x over here, and the nice thing we know here is that ln of e, they're opposites. That's gone. So you got negative x equals ln of 1.8. We can go on our calculator and do natural log of 1.8. Looks like it's about 0.8587. So now we got negative x equal to about 0.5, we'll round it here, 0.59. How do you find out what x equals then? Well, divide or multiply by negative, and it would be negative 0.59. That's approximately what that exponent is. So we're going to use that same line of thinking then to try some of these other ones out here. So let's look at this one. Same thing. Treat it like an algebra problem to start with. -2. Keep going until you can't go any farther using algebra. We can still go farther here. We can divide by 3. So we got e to the x equals. Now, if I take 2 divided by 3, it's going to be like 0.6666. I don't want to round that to 0.6. I'm going to leave it as a fraction here of 2/3. Okay, now how do we undo this exponential? If it's an E1, natural log both sides. And basically the natural log and e cancel out. So now we got x equals the natural log of 2/3. We can go on our calculator now and see what that equals. So type in natural log 2 divided by 3, and the answer is about -0.41. That would be what that exponent is there. All right, why don't you try number 8 out on your notes? You want to pause the video, see what you get, and kind of check and see how you do here. All right, let's see how well you've been doing on these. Start by treating like algebra problem. Add 9. Got 7. Looks like we're going to divide by 4 next. So if we divide both sides by 4, that cancels out. You got 7 over 4, which is 1.75. Now you get stuck here. This is the part where you can't really do any more algebra, so now you want to do logs. Natural log both sides. Okay, that lets us take our exponent and use log properties to write it there. Okay, ln of e, that's 1. So you got negative x equals, and we can do this on our calculator. If you do ln of 1.75, it's going to come out to be 0.56 about. And so multiply by a negative or divide by a negative, answer you should have got was about negative 0.56. That's how you can solve for exponents when you don't know the exponent. Now, where that's going to come up is some of these real life money problems or growth, exponential decay problems. Okay, so let's read through this one. It says, when interest is compounding continuously, that means all the time, the amount A in an account after T years is found by using this formula right here, where P is the amount of principal. Principal, just like we've been doing on a lot of these problems, is your starting amount. A is our ending amount. E's that natural number we've been talking about. R, if you can guess, is the same thing. That's your rate, your percentage rate. And T, like you could probably guess, is time. So, and number 9, it says, suppose you deposit $1,000 in an account paying 2.5% annual interest, compounded continuously. What's the balance after 10 years? Well, let's put everything in this equation. This is our deposit. That's our P, 1,000. E is just part of our equation here. 2.5%, that's our R. Remember, you got to change percent, though, to decimal. 2.5% as a decimal. If you move the decimal point over twice or divide by 100, is going to be 0.025. Our time is right here, 10 years. So it looks like we can just put this in and find the amount that's going to be there. So this is just a calculator problem. Type it in and see what you get. So on this one, type in 1,000. Hit second so you can get your E. Now it's in the exponent, so type in 0.025 times 10. And if we hit equals, we should get the answer. Looks like the amount of money in this account after 10 years is going to be about $1,284 and about 3 cents. Okay, not too hard. That was just a calculator problem. You'll see ones like this on the ACT. All right, and now the next part of this is a little bit harder. It says, how long will it take your balance to reach at least 1,500? Okay, that's the amount we want to end at. So now if we use the same equation and plug everything in, let's see what we get. We know the ending amount already is 1,500. We still have our starting amount of 1,000. E is always going to be in this one. Our interest rate hasn't changed. That's still 0.025. What we don't know now, though, is what's the time. We got to solve for that T. All right, so now we got to solve this one out. It's the variables in the exponent. So this is going to be a log problem. We can't quite do logs yet, though. We need to get this part with the variable alone first. So how do we get rid of the 1,000? Now, a common mistake is to go through and minus 1,000 here. No, we don't want to subtract 1,000. What's happening between our 1,000 and this E here? Multiplication. So the opposite of multiplying, we need to divide by 1,000. Don't subtract 1,000. Okay, so that divides out. Now you got 1.5 on the left side equals E to this exponent. All right, how do we solve this? Well, now we're stuck. We can't go any farther with our algebra. Now is the time to add in logs. And since we got E, we want to add in the natural log, ln. Okay, so now ln and E, we know those cancel out. They're inverses of each other. We got ln of 1.5 equals 0.025t. Now if you divide both sides by 0.025, we should have our answer here. So the amount of time is going to be whatever we get from this. So go on your calculator, type that in. Natural log 1.5, close the parentheses up, divided by 0.025, and it should tell us the amount of time it's going to take. It looks like it takes about 16.2 years. That's the amount of time we're going to need for that to grow to 1,500. Okay, hopefully you kind of got the idea now. See if you can use this and do some of those practice problems.